Good morning, students. Mr. Carver here. Today is section 5.5, bases other than E. We'll be differentiating and integrating. We'll start off with a few pre-calculus review topics. For instance, evaluating logs without a calculator. Log base 3 of 1/27. We can start off, as we've done in previous sections, by setting this equal to some variable. We'll call it x. And then switching it from logarithmic to exponential. This 3 then comes to the other side. Remember, logs are exponents, so the x is the exponent that sits on the base of the log. That is 3 to the x is equal to 1/27. If I give you a problem like this, which is no calculator, the idea is to get the bases to be the same. So I've got 3 to the x is equal to 1 over 3 cubed, which means 3 to the x is equal to 3 to the negative 3, if I just move that from bottom to top. So x is equal to negative 3 after I eliminate the base. Now, in this section, there's a handy property of logs that I'd like to review with you. It comes from pre-calculus that you'll use over and over again in this section. And that is the base change formula. Let's say that I give you, let's try this again, log base 5 of 7. And this is evaluatable using your graphing calculator. I think with the new operating system, you can actually open up the log option, and it does give you the option to enter your own base and your own larger number. However, the property that I want to talk about is the base change formula. And this is actually equal to log base 10 of 7 over log base 10 of 5. And incidentally, it doesn't matter what base you use. You could also do log base E of 7 over the log base E of 5, and you get exactly the same thing. And let me show you why. Let's say I take this expression right here, log base 5 of 7, and I set it equal to something. We'll call it y. I change it into exponential form. That is 7 is equal to 5 to the y. And then let's just say that I want to natural log both sides. This will give me the natural log of 7 is equal to the natural log of 5 to the y. By the way, I could have log base 10 to both sides, log base 2 of both sides. Base doesn't matter. I'm using this because it is a common base, and it's a base found on your calculator. I can then use properties of logs to move this y to the front. This will then give me the natural log of 7 is equal to y times the natural log of 5. And then, of course, I can divide through by the natural log of 5, and I get y is equal to the natural log of 7 over the natural log of 5, which is what we knew it would be using the base change formula. Now, again, I realize you can just plug this into your graphing calculator, but this process of using the base change formula is important in developing many of the formulas you're going to see in this section. For instance, let's start off with differentiation. All right, we'll start off with a couple of caveats. First, let's say that A will be equal to a positive real number, not equal to 1, and then U will be a differentiable function of x. Two formulas I need you to memorize. We'll put this in the red memorization box. The first one is, if I derive the first formula, I guess I should say, with respect to x of a to the x, this is going to give me the natural log of the base times a to the x. And then, of course, I want to derive the exponent, which is 1. And you'll see this when I write this more formally. The derivative with respect to x of a to the u. And again, u is something other than just x. What I get is the natural log of the base to the power, times the derivative of the power, which is what you see in the first line there. All right, now, before I work a couple of examples, I'd like to show you where this formula comes from. And, of course, it's tied into the base change formula. Let's say that y is equal to a to the x. And, again, just like I did before, I'm going to natural log both sides. And then also, in my previous proof, I took x down to the front, so this gives me the natural log of y is equal to x times the natural log of a. And now I actually have something that I can derive, right? And by the way, that's our goal here, right? We are deriving both sides of that original function with respect to x. And the reason I'm using the natural log of y, or the natural log of both sides, rather, is that I already know how to derive natural log functions, if you recall from first semester, or from earlier this semester, I should say. If I derive the left-hand side with respect to x, what I get is 1 over what I'm logging times the derivative of what I'm logging, which is 1 times dy dx. I'm implicitly deriving that side with respect to x. Now, on the right-hand side, it's a little more difficult to see, but the natural log of a is a constant. Remember, a is a real number other than 1. So when I derive that, I'm going to get the natural log of a times the derivative of the x portion, which is just 1. And now what I want to do is solve for dy dx. So I get dy dx is equal to the natural log of a times y. Goes from the bottom of the left to the top on the right. And then, of course, using substitution, what I get is the derivative of y with respect to x is equal to the natural log of a and times y, and y is a to the x. Of course, I've got the invisible 1 there, which, of course, is what we see on the previous page here on line 1. Natural log of the base to the power, times the derivative of the power. All right, and that's what I have here. Let's work an example. Let's say that I take y, and I've got 5 to the 3x. We'll start off with a very easy one here. I'm going to derive both sides. The left-hand side is going to be y prime, dy over dx. What I have then is the natural log of the base times base to the power, and of course times the derivative of the power. Now let me just point something out. This section is called bases other than e. What I'd like to point out, though, is that it doesn't matter what the base is. They could have actually skipped this section. So let me just cordon this off here. Let's just change it momentarily and imagine that that 5 is now an e. I just changed the problem completely. Is it possible to use the same formula? I have dy dx on the left-hand side, and what I could do is the natural log of the base to the power, times the derivative of the power. If you recall the natural log of e, that's the natural log of e to the first, which is really log base e of e to the first, and I did mention in a previous video. Those actually just cancel, so this portion right here is a little bit redundant. You don't need it. However, if you want to use it, you can, which means the formulas that you memorize in section 5.5 apply to any exponential function, whether the base is e or the base is not e. Now, of course, you've got to remain aware of all the previous sections, all the way back to chapter 2. So let's say I've got something like y is equal to x squared times 6 to the x cubed power. You're going to have to use the product rule here. So I've got y prime on the left-hand side. We'll start by deriving the first term there. That's going to be 2x times the second as is. And then I want to add that to the flip. So that's going to be the first underived times the derivative of the second. That is the natural log of base to the power, times the derivative of the power. All right, and we're not going to worry about simplifications. These really don't simplify very much farther than they actually already are, with the exception of maybe moving constant multiples out to the front. So we're going to let this be our derivative of y. And of course, just adding on here, let's say I changed it to, let's add this on. We'll do 1/2 of that product there. The only difference here is you would start with the outermost function, which is the root. So what you would do is derive that. That's 1/2 times everything inside as is. And then take 1 away from the power. And then you would go inside and multiply it by the product rule of the innards. So you would get, again, all of this. So essentially, if I just take this portion and put it right there in front, multiply those two quantities out, I get a more complex derivative of the original y. All right, let's derive some logs. We'll put this in the memory box as well, memorize box, rather. All right, let's say that I derive with respect to x. of log base a of x. Remember, a is a real number other than 1. What I'm going to get then is I get 1 over the natural log of a times 1 over x times 1. So it is 1 over the natural log of the base times 1 over what I'm logging times the derivative of what I am logging. And let's expand it out. More generally, log base a then of u, and u again is something other than just x, implying the chain rule. What I'm going to get is 1 over the natural log of the base times 1 over what I am logging times the derivative of what I am logging. All right, let me just show you where this comes from. Let's say that I've got just a very simple expression, log base a of x. On the right-hand side, these formulas essentially come from the base change formula. So if I just go ahead and jump straight to it, I've got the natural log of x over the natural log of a, which can be rewritten like this, 1 over the natural log of a times the natural log of x. And the reason I would write it that way is because, remember, a is a constant, so 1 over ln a is also a constant. So when I derive that, my y prime is going to be equal to the constant out in front, because that is the constant multiple rule, times 1 over what I am logging times the derivative of what I am logging, which gives me the first line up there. All right, let's work an example. Let's say I've got y is equal to log base 10 of the cosecant of 3x. You've got two options here. One is you can just go with this memorized formula over here that we have in the second line there, or you can use the base change formula. All right, and I'm going to choose to go with the formula because I've got it memorized. This is going to be 1 over the natural log of the base. And remember, this is the common base, right? If it's not written, but it is written as log, that is a base 10. So it's 1 over ln 10. This is going to be then times 1 over what I'm logging, which is 1 over the cosecant of 3x, times the derivative of the cosecant of 3x. That, again, is the chain rule. Cosecant goes to negative cosecant of 3x times the cotangent of 3x, of course, then times the derivative of the innermost function. And that is 3. By the way, they may clean this up slightly in the book. They could cancel those, which would give you 3 cotangent 3x all over, negative rather, all over ln 10. All right, let's take a look at another quick one here. We've got y is equal to t to the 3/2. This is log base 2 of root 3t plus 1. This is going to be a mess. All right, I think first of all, I'll change that root, and I'll change that to the 1/2 power to make this maybe a bit easier to see. My y prime then is going to be equal to, again, it's the product rule. This is 3/2 t to the 1/2 times the second as is. It's log base 2 of 3t plus 1 to the 1/2 power. I then want to add that then to the flip, the first underived, times the derivative of the second. It's going to be 1 over ln 2 times 1 over 3t plus 1 to the 1/2 power. And I'm going to go down here to continue this product, times the derivative of what I'm logging, which is going to be 1/2 3t plus 1 to the negative 1/2. Keeping track of what I've derived here. I've derived the log, I've derived the 1/2. Now I just need to follow it up with the derivative of the innermost function, which of course is going to be 3. So that's the sum of two products, rather lengthy products. All right, as we're working through this, I think I'm going to switch gears here, and I think I'm just going to keep this video to differentiation. I'll do a second video on integration. So let's talk about the last item that you're going to see in this section, and that is something like this. If I have y is equal to x to the 1 over x, you need to beware. You don't have a formula for a variable to a variable power. You have a formula for a real number to a variable power. You also have a formula for a variable to a real number power, but you don't have a formula for a problem like this, variable to a variable power, you have to use what they call logarithmic differentiation. Let me show you how this works. The first thing you're going to do is log both sides. So unfortunately, you don't have a formula for this. You've got to go back to what it is essentially the base change formula. All right, if you natural log both sides, and again, the reason we're using the natural log is because you know how to derive natural log functions. Also, I have the natural log of a variable to a variable power. This will not do. I'm going to use the properties of natural logs and bring that down to the front. So this gives me the natural log of y is equal to 1 over x times the natural log of x. And now I just have a simple product on the right-hand side that I can derive fairly easily. Let's continue this process. The left-hand side will be 1 over what I'm logging times the derivative of what I'm logging. That is 1 dy dx, because I'm deriving both sides with respect to x. And the right-hand side is just the product rule. So the first one there, 1 over x, I've got a couple of choices. And I think what I'm going to do is just move that to the top. That's x to the negative first, then times ln x. And I'll do the product rule with that because it makes the first term easier to derive. This is negative x to the negative 2 times the second as is. And I want to add that then to the first underived times the derivative of the second, which is 1 over what I'm logging times the derivative of what I'm logging. All right, I've got one more step for you. What I want to do is take this y and I want to move it to the other side because I want to know what dy dx is, and I want that alone. So the right-hand side will be negative x to the negative 2 ln x plus x to the negative 1 times 1 over x times 1. And that'll be times y on the right-hand side. Goes from the bottom of the left to the top on the right. But I don't want y there. I want to know what y is originally, and I want it to be in black, which is x to the 1 over x. This then is the slope machine, or the derivative of my original problem. So again, variable to a variable power. You don't have a formula for it. You must use logarithmic differentiation. All right, that'll be enough to get you through the first part of the homework. Thanks for tuning in, guys. Take care.